All right, well, welcome. In this video, we're going to be looking at lesson 6.3, specifically dealing with parametric applications. But before we get to that, I want to take a step back in time, and I want to review with you the type of problem that we saw back when we were learning about parabolas. Now, we've seen this type of problem not only in this class, but you've seen it in other classes previous to this one. But whenever we do parabolas, we will oftentimes incorporate it into it with a story problem similar to this one, where it says a distress flare shot straight up from a ship's bridge 75 feet above the water with an initial velocity of 76 feet per second. Graph the flare's height against time, give the height of the flare above the water at each time, and simulate the flare's motion for each length of time. Now, I'm not going to go through and do this actual problem. The idea here is to make a connection. Now, you might be wondering, well, how do we even come up with that equation that's in black there? How do they come up with that? Well, see in red, I have this equation. This is the equation we use to find the height of an object over a period of time. Now, g in this formula represents the acceleration due to gravity. Now, when we're dealing with feet, the value we use for g is 32 feet per second squared. And v sub 0 represents the initial velocity. H sub 0 represents the initial height. Now, when you look at that story problem, we're shooting the flare straight up from the ship's bridge 75 feet above the water. So that means your H sub 0 is 75. So that's how they got that on the end. The initial velocity is 76 feet per second. They just tell us straight up what that number is. And so we just plug that in for V sub 0. And our value for G, they don't say anything, but since everything's in feet, that's why we know how we know to use the value of 32. And so 1/2 of 32 is obviously 16. So that's where they came up with that equation. And what would we do with all those values, A, B, C, and D, for the 1 seconds, 2 seconds, and so on, is we would just plug those numbers in for T. And that would give us the height of the flare after that amount of time. Now, when we go to graph that, this is what the shape of the graph would look like. Now, sometimes when people see this graph, they just assume that this is the trajectory of the flare, that the flare is traveling in the shape of this particular parabola. But that's false. Remember, this flare is shot straight up. So in reality, if we didn't assuming that the boat wouldn't be moving and assuming there's no wind or anything else, the flare would go straight up and it would come back down again. So what this graph is illustrating is the height of that flare over a period of time. So the x-axis is not the horizontal distance that the flare is traveling. The x-axis represents the time since the flare was shot off and the height of the flare at that particular time. So we would see the vertex in this situation, the highest point the flare would reach would be 165.25 feet, and it would take about 2.375 seconds for the flare to reach that maximum height. So that's what we've done in the past. Well, in this unit with parametrics, what we're going to be able to do is use what we know to be able to create an equation to model the actual path of a projectile. That's not going straight up in the air and coming back down. So this has to be either kicked or launched or thrown or hit at an angle. So for example, please do not write down all this information on the slide. This is just, again, illustrating how we're going to come up with our different equations. So this first paragraph is just saying what I just said a second ago, that we're not dealing with throwing something straight up and down. We're going to be throwing or launching or hitting or kicking something at an angle. In this paragraph, they're just basically showing us how we're going to use this little illustration here. So what we're doing is we can use this information. So in this scenario, we're dealing with a baseball player throwing a ball. And so we can model the initial velocity by using a vector. So the vector that we would create, the initial velocity, we could put that in component form. So that's what this is showing. This is showing us that we could represent that vector in component form as v sub 0, the initial velocity times a cosine of theta, and the initial velocity times a sine of theta. And that diagram shows us how we would come up with that component form. So the equations that we're going to use. Now the textbook uses these two equations. Please do not write these two equations down. On the next slide, I'm going to show you how I want you to write these down. Because the way that the book does it, if you forget those parentheses, it's going to mess up your answers. So we're not going to write it like that. We're going to write it a little different. But we're going to use what they told us here so we can figure out how they came up with these two equations. So this first equation, That's summarized right here. The first equation, x equals v sub 0 times cosine of theta times time. Where are they getting that from? Well, that represents, that x component is simply, remember the distance formula. Distance is rate times time. So in this scenario, we're going to use the v sub 0 times a cosine of theta as your rate. So that's essentially like your rate. So we're going to take that component of the initial velocity times time. And that gives you the x component of your parametric equation. So we're going to look at that as being the horizontal position. That's going to be the horizontal position, which we'll get to in just a second. Now the other one, that looks very similar to that equation that we saw earlier, which again we see down here at the bottom of our screen. It's just that we're replacing v sub 0 with the y component from our component form, v sub 0 sine of theta. We're replacing v sub 0 with that piece to get that other equation. And so that's going to give us the vertical positioning. So here's what I want you to write down. So go ahead and pause this video and make sure that you get these two equations written down. Now again, I want to make sure I emphasize that the first equation represents the horizontal position of the object. The second equation represents the vertical position of the object. As soon as you understand and really grasp that concept, it's going to make answering the story problems a lot easier because you're going to know which formula to use. So write that down, pause the video. When you're ready to move on, go ahead and hit play. All right, so this is the story problem we're going to be working on. It says Kevin hits a baseball at 3 feet above the ground with an initial speed of 150 feet per second at an angle of 18 degrees at the horizontal. Will the ball clear a 20-foot wall that is 400 feet away? So essentially the question is asking us, did Kevin just hit a home run? That's what we're trying to find out. Now let's label this paragraph as far as what we know so we can plug in what we know into these two equations. All right. So it's talking about that he hit the baseball 3 feet above the ground. Now when he hits that above the ground, that represents our vertical positioning. So we're going to call that our y sub 0. Okay, so that's our initial vertical position that we had here. So that represents our y sub 0, that 3 feet. And then it says we have an initial speed, and initial speed is the same as your initial velocity of 150 feet per second. So that's our v sub 0. The 18 degrees, well, that's clearly our value for theta. And this part here, we're going to wait. We're going to wait on that because that's actually not part of our story. That's not part of the data that they're giving us to set up the equations. That's actually the question that we're going to start by answering first. But everything else we can use to put into our equation. So remember, look at your notes. We're going to set it up using these two. So we're going to start with the horizontal. So here's how we're going to set that up. Now, one thing, if you notice the way that I write my T's here, you might want to do the same in your notes, because if you wrote it the way that I normally write my T's, this is how I normally write my T's. Sometimes later when you look back at your notes, you might mistake that for being a plus sign. So I would highly recommend putting a little tail on the bottom of your T's. Make them look a little fancy. Go ahead and take this second to do that, and it'll make all the difference in the world later when you go back to look at your notes. All right, so that's going to give us the horizontal positioning of the baseball. Now let's come up with an equation that would give us the vertical positioning of the baseball. All right, so those will be our two equations that we're going to use to be able to solve this or answer this question. So the goal is to figure out, will the ball clear a 20-foot wall that is 400 feet away? So think about what they give us there. They give us two values, 20 feet and 400 feet. Now the 400 feet represents the horizontal distance from home plate. The 20 feet represents the vertical distance it is from the ground after a period of time. Okay, so there's two totals that they're giving us. And so we could put those totals into either one of those two places. So I could solve the equation, I could set up the equation rather, by putting 400 in my total for my horizontal distance and use that to figure out how long the time it would take to get for that ball to reach 400 feet away. Okay, so if we put 400 in the first equation, we could define the time in that case, and the time is going to be the same in both equations, so it doesn't matter which one we use. We just want to use the easier one. In the second equation, I could put 20 feet in there for y sub t as my total, and I could figure out how long it would take for the ball to reach a height of 20 feet. And then we could figure out, would it clear the wall at that point? So I could use either one. Now I'm going to use the one that's easiest. Again, I could do it for either one. But which one would be easiest? Well, clearly this first one would be the easiest. So what we're going to do is we're going to put 400 in for our total. And we're going to say that that equals 150t times a cosine of 18. And I want to solve for t. So if I solve for t, I'm going to divide both sides by 150 cosine of 18 degrees. Now go ahead and pause the video. Make sure that you do this correctly on your calculator, because when you do this, and don't just write it down, because I want to make sure that you know how to do this on your calculator. Because if you type it in wrong, if I just typed in 400 divided by 150 times the cosine of 18, chances are you're going to get the wrong answer. You want to make sure that when you type this in your calculator, if you do it all in one piece, put the entire denominator in parentheses. So your calculator knows to take 400 divided by that entire value in the denominator. All right, but when you do that, you should get 2.804 seconds. So what we just found is that it would take 2.804 seconds for the ball to travel 400 feet. Okay, so we know that much. But now, how high is it going to be after 400 feet? Is it going to be high enough to clear the wall? So now what we're going to do is we're going to take and put that time into the other function. Because by doing this, whoops, and I forgot my square, so if you caught that, thank you. But by doing it this way, by plugging this in, this is going to tell us the height of the ball after 2.804 seconds. And when you plug that in your calculator, you get 7.17 feet. So after 2.8 seconds, the ball is coming back down, but it's only going to be a little over 7 feet above the ground. So that does not clear the fence. So it is not a home run. Sorry, Kevin. All right, so that's how we would answer part A. Now I'm going to give you a hint. Parts B, C, and D kind of all relate to each other. Let's look at how we would do those. Now we're going to still use those same two equations. So you should already have those written in your notes. But this one is asking for what is the maximum height the ball reaches and when does it reach its maximum height? Now remember, the trajectory the ball is traveling is in the shape of a parabola. So I want you to think to yourself for a second. What is this question? What part of the parabola is this question asking us to find? Hopefully you're thinking that this is asking us to find the vertex. And recall, when we have an equation in standard form, if we want to find the vertex, the x part of the vertex we find by taking the opposite of b over 2a. To find the y part of the vertex, we just put that value back into the function, and that gives you the y part of the vertex. All right, so how does that translate to this problem? Well, for this problem, the time is our input. So to find the time, we would take the opposite of b over 2a. Now we got to ask yourself, well, what's b and a in this problem? Well, a is easy to find. Again, this is in standard form, so our a value is negative 16. You don't include the variable because we're just looking for the coefficients here. I want you to look and see if you can figure out what our b value is going to be. Is it 150? Is it sine of 18 degrees? Is it both? Well, if you said that it's both, you are correct. So it's not just 150, it is the entire piece. Remember, the b value is a coefficient for that middle variable. And the coefficient would be 150 times the sine of 18 degrees. Now we don't need to use c in this part of the problem, but c would be 3. All right, so let's plug these numbers into the equation. So it's going to be the opposite of b. So the opposite of 150 would be negative 150 sine of 18 degrees, all divided by 2a. A is negative 16, so 2 times negative 16 is negative 32. Now when I plug that in my calculator, again, I want you guys to pause the video. Make sure that you can plug this in on your own and get the correct answer. You should get 1.45 seconds approximately. So what we just found is actually part B. We found the when. The when is referring to time. So anytime you see when, it's referring to the value for t that we need to find for that. now, how do we find the what? How do we find what is the maximum height the ball reaches? Well, remember our two formulas. Remember, this one here gives us the horizontal positioning of the object. This gives you the vertical positioning of the object. So we want to find the maximum height. Well, that's referring to a vertical position of the ball. So we're going to use that second equation. So we're going to plug that time in, 1.45 seconds, to figure out after 1.45 seconds, that's when it reaches maximum height, what would be the maximum height? So that's how you set it up. So again, this is going to give us what the maximum height is, because we would use that second formula, because that formula gives us the vertical positioning of the object. So in this case, the vertical position of the ball. And when you plug that in your calculator, I'll just tell you, you end up getting 36.6. 36.6 feet. All right, now the next part, part D, asks us for how far away from the initial hit is it when it reaches its maximum height. So we're going to use that same time. So remember, reach the maximum height after 1.45 seconds. Now this is saying how far away from the initial hit. So this is asking for the horizontal distance from home plate. So we're going to plug that 1.45 into our horizontal position formula, which is this one. And this you just plug in your calculator. This one's pretty easy to plug in your calculator. When you do that, you get 206.85 feet. So after 1.45 seconds, it would be 206.85 feet away from home plate when it reaches its maximum height. Let's go ahead and, even though it doesn't ask us to do this, let's go ahead and sketch what our shape of our parabola is going to be here that we're working with so far. So let's see what we know. So let's say this is the trajectory the ball would have traveled. So this is where it's hit. So it's hit from a height of 3 feet. So remember, at about 400 feet, we know that it reached a height of 7.17 feet and it hit the wall. So that vertical line there that I drew, let's pretend that's the wall. We just found that the maximum height, let's say is right there, is after 206.8, or it's 206.8 feet from the wall. And this would represent the height at that point, which was 36.6 feet. Okay, so that's what we know so far. That would be the trajectory that the ball would have traveled. Now in the next part, it's going to ask us for when does the ball hit the ground. And we might also want to know, well, how far away from home plate did it hit the ground? So let's pretend you could take away that wall. So let's say maybe he's playing baseball out in a field instead, where there's no wall, there's no fence to clear. He just hits it and it follows that same trajectory. You want to figure out how long and how far did it travel. That's what we're going to do next. Well, when you think about it, this point here would be an x-intercept. So can you think of when it hits the ground, we're trying to find the x-intercept. Remember, there's a formula. We're working with quadratics. There's a particular formula that we use to find the x-intercept. Can you think about which one that is? Well, hopefully I gave you enough hints there for you to remember that we're looking for the quadratic formula. So the quadratic formula, oops, fix that. The quadratic formula would be this. It'd be the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. In this case, instead of using x, you see that we're using t, so that's how I know that I'm going to use that formula. Or that's how I know to solve it for t instead. So we'll have the x-intercept or the t-intercept would be opposite of b plus or minus the square root of b squared minus 4ac all over 2a. Now remember, we have our values for a, b, and c. We found that on the previous part. So we have a we know is negative 16. B is the 150 sine of 18 degrees. But you know what? To be honest, I don't want to put b into both of those places as 150 sine of 18 on my calculator. That's just going to be a real pain. So instead, I'm going to simplify 150 sine of 18 degrees and just find that to be 46.35 approximately. My value for c is just 3. All right, so we're going to plug this information in to that formula. All right, so it'll be negative 46.35 plus or minus the square root of 46.35 squared minus 4 times a, which is negative 16, times c, which is 3, all over 2a. So again, a is negative 16, so this would be negative 32. Now, when you go to simplify that on your calculator, you might want to do that in a couple of steps. If you type in the square root button first, it's going to give you a parentheses. So just make sure if you do that, wait to close it off until the very end. So maybe instead of using parentheses here, you could use times button instead of using parentheses, just to make sure that you don't mess it up. Otherwise, if you're worried about that, you could just do what's underneath the square root first and then take the square root of that larger number. But either case, when you end up doing that, you should, again, try this on your own to make sure that you do this correctly. You should get 48.38 approximately. So we're going to have two solutions, one that we're going to use, one that we're not. So let's start with the plus. So if I took negative 46.35 plus 48.38, I'm going to get a positive number, but when I divide by negative 32, I get a negative 0.063, which we really don't care about. Because we don't care about the negative time. We're not going back in time. That's what we're finding here. We're finding our value for t. So to find the answer we're looking for, if I take negative 46.35 minus 48.38, it's going to be a bigger negative number. But when I divide that bigger negative number by negative 32, it gives me a positive 2.96. So when does the ball hit the ground? It's going to hit the ground after almost 3 seconds, after 2.96 seconds. Now, they didn't ask us this, but this will be helpful in your homework assignment. Also answer this question of how far? How far did it travel when it hit the ground? So to figure that out, since we're using the question of how far, that's referring to the horizontal distance. So we're going to use that equation. Oops, not F. Where it was 150 times the time times the cosine of 18 degrees. It's just that now we're going to put that 2.96 in for our time. And when you do that, you get your final answer, and so your answer for that would be 422.33 feet. So that's another type of question that they could ask in your homework assignment. So hopefully that helps, and that is the end of our parametrics applications. So good luck as you work on your assignment.